So the next topic is strong, moderate, and weak electrolyte. Okay, or weak acid, you can say. Okay, so when we are talking about strong, moderate, and weak, so these are what parameter? Actually, these are the relative parameter, no? So this actually indicate how strong an acid is or how weak an acid is. Okay, so basically there are the previous video we have some idea about the definition of acid. Okay, so according to actually Bernstein and Lowry theory, so we know that an acid can donate what? Proton, okay, to any substance or any solvent, okay, and then and a base can what? Accept that proton, okay. That means acid can donate a proton and the base can accept that proton. This is the main concept of Lowry and Bernstein and Lowry concept, okay, or the definition of Bernstein and Lowry concept. So here actually when the acid is dissociated, actually when acid will going to lose a proton, then the remaining part is actually their what? Conjugated bases. We have already discussed this one, no? So let's suppose we have an acid. Let's suppose this acid HCl. HCl is an acid. So suppose we add this one in water, okay, and because this is an acid, so what will going to happen? It can donate some proton, okay, to that base, so it will become what? So the proton will be accepted by this water, okay, so it will become H2O positive, okay, understand? So now the thing is that what is the remaining part? Remaining part will be your Cl negative. That means here you see these two will be, these two are actually they are related by what? By a hydrogen is by a S positive ion, okay. So when a S positive ion will going to added to this Cl negative, then we will get back this one, okay. So they are, that means they are conjugated, okay, they are conjugated with each other, okay. So this one is, since this one is acid, that means this one can donate proton, no? So this one is acid, so let's suppose this one is acid, so the conjugated part is known as what? The conjugated part is known as, since this one is acid, so it will be what? Your base, okay. So that means conjugated acid and base, okay. Similarly in this case also they are related by what? H positive ion. So when H positive ion will be accepted by this water, then it will going to form this one H2O positive hydronium ion, okay. Since this will going to accept H positive ion to form this one, so it is your base. And here to get this one from this one, actually that means hydronium ion must lose H positive ion, so it will be your acid, okay. So that means this is your, let's suppose we just mark by using one subscript 1, okay, such that this is the one pair conjugate acid and base, and this one is the other, okay. So the thing is that now now interestingly, the thing is that when this is, we know that actually the strength of a acid or a strength of a base is depend upon actually how fast they will going to generate that proton, okay. So acid strength will depend upon what? Acid strength will be depends upon the how fast actually this will going to generate that H positive ion, okay, or how fast that acid will going to um, give, or how fast that this acid will going to give this H positive ion to the other solvent or some other bases, okay. So if the acid can easily, or if the acid can easily generate this H positive ion, then the acidic strength of this one will be high, understand? Or similarly in case of base, let's suppose sodium hydroxide, or let's suppose this water, how fast this water can actually able to take this H positive ion, okay. If this H2 that means this water can accept the H positive ion very fast, okay. If the water can accept the H positive ion easily, okay, with a very fast rate, okay, then the strength of the base will be high. That means the basic strength will be this water will be high. That means this will be your strong base. But in this case, you see, as if you consider this reaction, okay, so here you see actually the water HCl is a very strong acid, okay. So that means what, it can easily donate H positive ion to that water, okay, understand. So if it can donate easily H positive ion, that means that acid is your very strong acid, okay, strong acid, okay, understand, strong acid. But the thing, the concept, this concept is very important, okay. If the one, here you see, here this one and this one is your what, they are related, okay, actually this one and this one actually what, they are conjugated acid and base pair, no? So if one of the pair, that means one of the conjugated pair, if one of the conjugated pair is a strong, then other part will be your weak, understand, clear. So if this acid is your strong acid, then the base, that means the conjugated base of that acid will be your weak, okay. If it is strong, then it will be weak, understand. So again here you see this, in case of this H2O positive, actually H2O positive is a very strong acid, okay. So if it is strong, then it will be your weak. So water will be your weak base and H2O positive will be your strong acid, understand, clear. So that is the concept. Actually this concept is actually coming from what, the Bronsted and Lowry concept, okay. So always remember this point, okay. What is the point? The point is that in case of conjugated pair, if the one of them will have strong, if the one of them will be strong, then the other will be your weak, okay, clear. So this is the main concept, okay. So similarly, that means you see, that means here also you can also observe this equilibrium, okay. So what about this equilibrium? So since the thing is that since the HCl is a very strong acid, okay, so that means the rate of this this forward rate will be very high, okay. That means it will going to easily donate the H positive ion to the water, understand, and it will going to form that Cl negative ion, clear. But here you see, since this base is a very weak base, so the reverse reaction is a very small, that means the rate of the reverse reaction is negligible, okay. So that's why we can write only one directional, or we can actually write one headed arrow instead of double headed, sorry, double headed arrow, actually one directional arrow in instead of this arrow, instead of this arrow, okay. That means reversible arrow, clear. So if, always remember, if the electrolyte or the acid or base is a strong one, then we have to write only this arrow, okay, one directional arrow, not the reversible arrow, clear. So this is the main point, okay. So let's now again take one more example, okay. One more example of a weak acid. Let's suppose weak acid is CH3COOH. So we know that this is an acetic acid and this is a weak acid, okay. So let's suppose it will going to react with water and it will going to give you what. So because this is an acid, okay, so that means it can donate H positive ion, and that H positive ion will be accepted by that solvent, no? Water. So it will act as a what, base, because it will going to accept that H positive ion, okay. So it will become H2O positive, this water will going to become H2O positive by taking this, by accepting this H positive ion, okay, clear. So plus the remaining part will be what, CH3COO, CH3COO negative, understand. So actually this one is what, this one is actually the structure of this one is actually this, like this, okay. CH3COOH, okay. So actually since the electronegativity of O is higher than oxygen, so that the two, here two electrons are there now in one bond, this is the covalent bond. So one electron is coming from here and one electron is coming from here, so they will going to share these two electrons to form this bond, okay, covalent bond. But here when this bond will going to break, then this actually this cleavage of this bond is what, heterolytic. Okay, heterolytic cleavage. Okay, so it will going to, the two electron will come to this part, so it will become positive, this will become positive, and this will become negative, and this bond will going to break. Okay, understand? So as a result we are going to get CH3 COO negative. Okay, and this H positive will going to accept by this water molecule to generate this H3O positive. Now the thing is that here again you see CH3 COOH, that means acetic acid, and this one acetate ion, they are actually related by what, the H positive ion. Okay, so here if you add H positive ion, you will again get back this one. Okay, that means they are conjugated acid and base pair. Okay, so here since this one is acid, then the other one will be what, base. Okay, base. So this one is just suppose 1 and 1, just to represent this, represent that they are related, or they are what, conjugated acid and base. Okay, pair actually as conjugated acid base pair. Similarly this one also, this one also conjugated acid and base pair. Okay, so here we know that the acetic acid is actually weak acid. Okay, since this is a weak acid, that means this will be your what, strong base. We have already understood this one, no? So if, since this one is your weak acid, okay, that means its conjugated pair part will be what, the conjugated pair will be what, strong. Clear? So that means this forward reaction rate is not so high. Okay, so that means we can write here, since this is your weak acid na, so we can write the reversible reactions. Okay, so we can use that reversible symbol. That means the forward reaction rate is not so high as this one. Okay, because this one is very high, because this is a very strong acid. Okay, but this is not a strong acid, it is a weak acid, so the dissociation of this actually acid into their ions will be not so fast. Clear? So in case of weak acid, we can only use the concept of ionic equilibrium, because here in case of only reversible reaction we can use that equilibrium concept. Okay, always remember that point. In case of reversible reaction, only we can use equilibrium concept, because equilibrium will be exist only in case of reversible reaction. Okay, not in not in the unidirectional reaction. Okay, clear? So the general rule is actually, the general rule, we can conclude this, we can conclude these things in by using one sentence, that the general rule actually, the stronger, remember this point. Okay, the stronger, okay, so let's use some new pages. The stronger an acid, the stronger an acid, comma, the weaker must be its conjugate base. Okay, and vice versa. Okay, vice versa. Okay, understand? This is actually the main concept. If you know the strength of one one acid or one base, then you can have the idea about their conjugated acid or bases. Okay, if the acid has if the acid is strong one, then their conjugated base will be your weak base. Okay, clear? So actually in case of water, if you consider water, then what will be, what about water actually? Is water is a weak acid, or is water is a weak base? So the question is, what about water? What is water actually? Water is a weak acid or weak base? So actually water is a very weak base, because its conjugate acid hydronium is a very strong acid. Okay, so if you consider this one is H2O, then actually when it will going to, let's suppose it will going to take some H positive ion from acid, okay, let's suppose, okay, then it will become what, H2O positive. Clear? So actually this H2O positive is a very strong conjugated acid, okay, remember this point. So, conjugated acid, so that's why water is a weak base, okay, so that means water is a what, weak, so water is considered as weak base, okay, clear? So at the same time water is a very weak acid also okay, this is a weak base, also it is a weak acid. Why weak acid? Because its conjugated base is very strong base, because you see in case of water actually it can dissociate into this, so okay, so here this OS is actually very strong base, okay, so if this is a very strong base then it will be what, weak acid, okay, so that means water can act as a weak base, also it can act as a weak acid, okay, clear? So this is the main concept, okay, that means water can show the both properties, okay, so that means we can use the reversible symbol, or that means reversible reaction, we can observe reversible reaction in case of water, okay, because it will be your weak base or weak acid, okay. So now next point is actually the strength of the acid is also, acid or base will be also actually depends on the solvent also, okay, so if you use, let's suppose, if you, let's suppose this is you will going to use some acid, okay, in some solvent, okay, as well as solvent, so if the solvent will not going to accept that H positive ion easily, then that acid will be not your strong one, okay, understand? No, it will not going to act as a strong one, even if you, let's suppose in HCl here water, okay, if in, let's suppose it will going to give H2O positive plus Cl negative, okay, the same HCl if you take in benzene, okay, benzene, BENZENE, okay, benzene, so I am a very lazy one, okay, benzene, so try to write this properly, okay, HCl, so H, when you uh, add this same HCl, okay, in different solvent, then it may not be, it may not show the same strength, that means it may not be act as a strong acid, maybe this benzene may not, this benzene cannot accept the H positive ions you know easily as water, okay, so the acid, actually the acidity or the strength of an acid or even a strength of a base is depends upon actually the solvent, okay, so if the solvent has the property, or they can accept the proton or the OS negative ion, or proton, or sorry, proton is positive ion, or it can donate is positive ion easily, then the acid will be, or the base will be strong one, okay, they will going to behave as a strong one, clear? So this is actually, that means that means the what that means the actually solvent also going to influence the strength of a acid, okay, clear? So this concept is all the concepts are coming from which law, or which concept? Actually from the Bernstein and Lowry concept, this all the concepts are generated, okay, so that's why the Bernstein and Lowry concept is very important one, clear? Okay, so now coming to the new one new topic, which is your dissociation of acetic acid. So let's discuss about this one, okay, the dissociation of acetic acid, okay, acetic acid. So acetic acid is what? Acetic acid is actually um your weak base, no, sorry, weak acid. So even this is what, actually this is your weak acid, okay, so if you add the acetic acid, let's suppose CH3 COOH, this is acetic acid, no? So if you add this acid, but this is a weak acid, okay, with a very strong acid, let's suppose it is a very strong acid, okay, this is, so it will behave as a base, okay, because compared to this one, the acidity of this one will be higher, let's suppose. Okay, so that means this can even act as a base, that means solvent, act as a solvent. Okay, so in this case, so it will going to give you what? It will going to give you, let's suppose, CH3COO. So it will going to act as a what? Base, na? So it will going to accept that H positive ion, so it will become H2 positive. Clear? Plus the remaining part will be what? A negative base. That means this is your acid, that this will be your base. Okay, so this is your strong acid, this will be your weak base. This is your strong. Okay, so this is your strong, sorry, weak. It will going to act as a weak base, but it will going to act as a what? Strong acid. Okay, understand? But the thing is that see here, actually this is a very weak, actually acetic acid is a very weak acid. Okay, so this forward reaction rate is very small. Okay, the rate of this reaction is very small compared to the backward reaction. Okay, so it is very hard to observe these products. Okay, clear? So this, in case of dissociation of acetic acid, that means in case of if we add acetic or a very strong acid in acetic acid, then we can, there is a possibility to get this type of or there is a possibility to exhibit this type of reactions. But the thing is that the forward rate reaction is very small because of the nature that it is a very weak base. Okay, so I think up to this one we able to understand that the strength, that means whether a acid will be strong or whether a base will be strong or weak. Okay, it is depends upon what? It depends upon actually how fast they will going to, how fast the acid will going to donate a proton, or how fast and base will going to accept a proton. Okay, if they can accept or donate proton very easily, or very in a faster, okay, in a faster rate, okay, then that acid will be your strong acid. That means they can easily donate that proton, okay, in a faster rate. Or that base will be strong base if that the base can accept that proton easily. Okay, so this is and the moderate acid and base will be what? In between them. Okay, clear? And always remember that the strong acid or strong base, we cannot use the equilibrium concept. Okay, because there will be no any reversible reaction, because only one dimensional or one directional reaction will be observed in case of strong acid or strong bases. Okay, so when we are talking about ionic equilibrium, that means we have to consider weak acid and weak bases. Okay, now let us discuss about a new important topic. Okay, this is actually known as leveling effect. Leveling effects. Okay, so actually what is leveling effect? So here actually this is coming from the dissociation of water. Okay, so in comparison to the acetic acid, water is actually stronger, okay, stronger base than acetic acid. That means if you consider a acid, let's suppose this one, then in water, then it will actually going to give you H2O positive plus your A negative. Okay, so this is your base. That means water will going to act as a stronger base than this acetic acid, because in acetic acid, you see, this is no doubt this will act as a base, but this is a very weak base. Okay, so the forward reaction will be not so good. Okay, but here water is a very stronger base than that acetic acid. Okay, so it will going to eventually give that H2O positive and A negative. Okay, if this is a strong acid. In other words, what we can say, that water the water actually can accept proton more easily than what? This acetic acid. Clear? So actually one important thing is that we have missed one point in case of dissociation of acetic acid. Actually in case of acetic acid, let's suppose we are taking this reaction, HA plus CH3 COOH. So this is your acetic acid. when we add some strong acid with acetic acid, then they will going to form what? Then they will going to form your H2 opposite. No, sorry, this will going to what? This is your base, na? So it will, since this one is your base, so CH3 COOH2 positive, okay, plus A negative, na? But here the reversible reaction sorry, the forward reaction is lower than the backward reaction, na? Right. So here if you use different acids, like let's suppose HTO, HClO4, hydrogen bromide, okay, H2SO4, okay, HCl, or nitric acid, HNO3, okay. So if you add this acid in that glacial acetic acid, this is actually acetic acid or glacial acetic acid, so then that they will going to what? React with acetic acid, and they will going to form that base, or that means um, this acid will going to what? Donate electron to donate proton to that acetic acid, no? Because they will going to act as a base, or in other words, what you can say, this acetic acid will going to accept protons from these acids, okay. So how fast they will going to accept the proton, so it will going to determine their what? The acidic nature, okay. So if you use some conductance measurement, then and calculate the strength of the acid, then actually the strength of the acids, these acids in glacial acetic acid, is found like this one, okay. So that means the the strength of the this acid is higher than this one, hydrogen bromide, then sulfuric acid, then hydrochloric acid, then nitric acid, in what? In acetic acid. But in case of this one, but here if you coming to the water, if you add the same acids, let's suppose this 1 2 3, this acids, okay, this acids in water, so HA is, let's suppose HA is your, these are, okay, this represents the HA, okay. So if you used this acids in place of HA, and in place of HA in what? Water, okay, and you can calculate their conductance measurement, okay, and by using that conductance measurement data, you can calculate their strength, okay. So in this case, what will going to happen? Because this is, you see, because water will be act as a what? A very good base, okay, in comparison to the acetic acid. So what will going to happen? The all the acids will going to act as a or all the acid will going to exhibit the same strength, okay. That means this they all will going to give the same strength. That means what? That means HClO4, the strength will be equal to the SBr is equal to the sulfuric acid is equal to HCl, or is equal to nitric acid. Or what we can say in other words, we can say that in water, this all the acid will going to uh, act as an what? Act as an strong acid, no doubt, strong acid, but the strength of that all of them will going to be same. That means the strength of all of the acid will going to be same. Understand? Clear? So this effect, actually this actually this water will going to level level of this all the what? Strength of the all acid equal, na? They actually, this water will going to equalize the strength of all the acids, okay. So that's why this is known as leveling effect, okay. This effect is known as leveling effects. Clear? So however, the ionic equilibrium in water do not proceed so far in the case of weak acids like formic acid, acetic acid, propionic acid, lactic acid, tartaric, or phosphoric acid, okay. It is therefore possible to distinguish between the relative strengths of these acids in aqueous medium only, okay. Clear? So mainly the concept is that the water will going to level of the strength of all the acid, or they can actually, water will going to equalize the strength of the all acids, because the water will going to act as a what? A stronger base than acetic acid. This is the main concept, okay. Now before going to discuss about the new topics, let us now introduce the new definition of acid and base, okay. Actually we require new definition, because many acids and bases are there which don't have any H positive, or is which actually cannot donate H positive ion, or which cannot accept H positive ion. Okay, so how we will going to determine their state, or how we will going to define those materials, okay, or those substances, whether they will going to act as a acid or base. So actually in 1923, a scientist named G.N. Lewis, actually he introduced a general concept of acid and base. Okay, so according to him, actually an acid is a species, okay, that is capable of accepting a pair of electrons from a covalent bond. Okay, so what is the definition? An acid is a species. So let's suppose this is a acid is a species which can which can accept electrons pair, so which can accept electrons pair, okay, from a covalent bond, and a base is a species that is capable of donating a pair of electrons to form a covalent bond. Understand? So they will going to acid will going to accept electron pair from a covalent bond, and the base will going to donate a electron pair to form a covalent bond. Okay, so there are many examples. Okay, many examples are there. So you can go through the Puri Sharma and Pathania book, the page number 711. Okay, 711. There are many examples are given, so I am just going to give you one example. Okay, so let's suppose this one, BF3. Okay, BF3 with ammonia. Okay, so actually this one is very known molecule. Okay, ammonia. Actually this is we studied about this ammonia in class 11 or class 12. Okay, so actually the structure of ammonia is like this one. Okay, actually they have a lone pair. Okay, so if you uh, try to try to draw the electronic configuration, okay, then you will going to get that there will be a lone pair in that nitrogen. Or you can also, actually this lone pair, actually you have to this lone pair is actually one of the hybridized orbital. Okay, so you have to know the hybridizations also. Okay, so what is the hybridization? So actually sp3 hybridization is this one, is actually sp3 hybridization. Okay, so there will be 1 2 3 4 4 sp3 hybrid orbitals are there in that nitrogen, and 3 will going to form bond with hydrogen. Okay, that means 3 sp3 hybridized orbital will going to overlap with the atomic orbital of hydrogen to form that this 3 covalent bond. Okay, and the remaining 1 sp3 hybrid orbital will have the lone pair. Okay, that means, and this lone pair can be donated to the other material. So that means this will going to act as a what, base, because they can donate, and by donating this one they can form a covalent bond. Clear? So similarly, this in case of this BF3, so if you draw the structure, which, so it will be like that. Okay, actually it is you have actually, I think, gone through these things in higher secondary classes. Okay, let's suppose this is coming from the fluoride, and this is coming from the boron, because boron has how many electrons? 3 electrons are there. Okay, in outermost orbitals, boron has 3 electrons. Okay, so try to find out it by yourself. Okay, so what is boron configuration? You can do you know how to write configuration? I think you know how to write configuration, no? So here actually in case of boron, there will be 3 electrons in the p orbitals. Okay, that means like this. In the p orbitals there will be 1 2 3 electrons will be there. Okay, so these 3 electrons actually 1 2 3, and this electrons, cross electrons, actually this represent actually the electrons of fluoride. Okay, the outermost electrons. So they will going to share this electron. One electron will come from the fluoride and one fluorine, and one electron will come from the boron, and they will going to form a covalent bond. Similarly this one and this one also. Okay, so here actually there will be some vacant side will be there, because you see 1 2 3 4 5 6, so 6 electrons will be there in the outermost orbitals. Okay, but we know that to become stable it needs how many electrons? 8 electrons, because to get that noble gas configuration. Okay, So that means this will going to act as a what? Acid. Why acid? They can accept electron. Okay, they can accept one lone pair of electron to gain the nearest noble gas configuration, okay, to become stable. Clear? So similarly here, in case of ammonia, here 1 2 3 4 5 6 7 8, actually nitrogen had 1 2 3 4 5 electrons in the outermost orbitals, okay, and here this dots represents the electrons from hydrogen. So this is a single bond, single bond, single bond. I'm not going to explain this thing, okay. This is the covalent bond, this is covalent bond. This is actually you have gone through in high secondary, okay. So here this actually this one is what? This one is actually coming from nitrogen. This actually coming from nitrogen, okay. So actually the electronic configuration of nitrogen is what? 1s2 twice s2 twice p plus p what? 3, because you see hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, no? So it will be 1 2 3 4 5 6 7. So 7 1 2 3 4 5 6 7 7 electrons. So it will be, the configuration will be like this one, okay. So outermost electron, how many outermost electron will be there? So you see this one is 1s twice s twice p, okay. So twice 1s is, this is your inner orbital, okay. So outermost orbital is 2, this is 2s 2p. So why outermost orbital? Because here the 2 represent what? Principal quantum number, okay. Now this is your principal quantum number 1, okay. So here the outermost orbital is twice s and twice p, okay. So here how many electrons are there? 3 plus 2, that means 5 electrons will be there, no? So it will be how many? 1 2 3 4 5 electrons will come from the nitrogen, and the others will be 1 1 from the hydrogen, and this will go to covalent, single bond, single bond, single bond. Clear? And that means there will be some one lone pair which is actually available for donation. That means they will going to act as a what? Base, okay. This ammonia will going to act as base. So they can actually, this electron can donate it, this actually this electron pair, actually this ammonia can donate this electron pair to the this acid, because this acid can accept the electron pair, okay. Then finally they can form what? They can form the, so we have no more room now, so we can just cut this part. So they can actually, by reacting this one actually, okay. So let's go to a new page. So we have this one B F, okay. So this one, let's suppose your bond, and this is nitrogen, hydrogen, 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 okay. These are 2 electrons. So these 2 electron pair will be donated from here to here, okay, and they will going to form the bond, okay. So F dot B, this is the normal part, okay. This is F, and here they will going to share the electron, okay. So 1 electron will come from what? The nitrogen, and 1 electron, actually these 2 electron will come from the nitrogen, okay, nitrogen, and this is your hydrogen, 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 okay. Clear? So they will going to form the covalent bond. So that means here we observe a reaction. The reaction, we can write the reaction like this, okay. B F3 plus NH3 F3B, and here NH3, okay. So that means this will going to act as a what? Acid, okay, and this will going to act as a base, according to what? According to that Lewis concept, okay, and they will going to form a molecule. Understand? Hope you understand this concept of the new definition of acid and base, by on the basis of the accepting a electron pair or a donation of electron pair by the molecule, okay. So if a molecule can donate electron pair and form a new covalent bond, then that molecule will be what? Base, okay. If a molecule can accept electrons pair and form electrons pair from where? From a covalent bond, or it may be from any other bond, okay, then it will be act as a what? Acid, okay. And the strength of the acid will, or the base will be depends upon what? How fast that acid will going to accept the 2 electron pair, sorry, 1 electron pair, that means 2 electrons, or how fast the base will going to donate the lone pair to that to the acid will going to determine their strength. Okay, if they can accept, that means if the acid can accept the lone pair easily, okay, then the acid strength will be high. Okay, similarly if the base can donate the electron pair easily, okay, then the basicity of that base will be high. Simple thing. Okay, so this is actually the definition of Lewis concept. Okay, actually by using Lewis concept we can define acid or base like this way. So that means from this study, okay, from this study what we learned, actually we learned that the strength of a acid or base, okay, we can define the strength of a acid and base by using Bronsted and Lowry concept. Okay, so which is actually discussed now, by actually using that concept how fast the proton will going to be donated by that acid, or how fast the proton will be accepted by that base. Okay, that one was your first concept, and now this one is your Lewis concept based on what? Electron pair. Okay, hope you understand this strong, moderate and weak acid or base, that means the electrolytes. Okay, so now actually in the next class we will going to discuss about mainly the degree of ionizations and factor affecting degree of ionizations, ionization constant and ionic product of water. Mainly we first of all we will going to discuss about first of all mainly we will going to discuss about dissociation of weak acids and bases. Okay, and when we're going to discuss that topic now, dissociation of weak acids and base, then in that topic actually we're going to uh, we're going to get know about, we will going to know about some new topics like dissociation constant or degree of dissociation. Okay, and also k alpha and alpha. Okay, so for today I think it is sufficient. Okay.